Welcome to week 4. This week we'll get going with hypothesis testing with t-tests, and then the second part of this week we'll start with one-way ANOVA, which will continue ANOVA into the following week, but this will help get us started for sure. So when we talk about t-tests, we've set the stage a little bit by looking at our descriptive statistics, looking at standard error, those kind of things. So for a t-test, what we're really interested in doing is comparing two means to see if they're significantly different from each other. So if you recall your previous homework from the other week with the CEO salary data set, I had you run descriptive statistics on the whole data set, then do a split file command, run descriptive statistics for men and women separately, and just asked you kind of if you noticed any pattern or trend. So you probably noticed that the salary for men was quite a bit higher than for women. So that's interesting from a descriptive standpoint, but when we get into our hypothesis testing, the question is, are those two salaries for men and women statistically significantly different from one another? We know they're different, but how discrepant do those need to be for us to say that they're statistically significant and something is going on in our data? So that's kind of setting the stage for our t-tests and where we're headed for this week. So a couple of points about our t-tests. And this is why we've really been hammering this idea of independent and dependent variable and different units of measurement up until this point. Because a t-test must have an interval dependent variable, so something you can take the mean of. So something like salary, IQ, height, weight, job satisfaction scores, personality traits. It has to be something that we're able to take the average of. And then our independent variable, or our predictor, it must be a nominal or categorical variable that has two levels. So in the example that I just mentioned, we have CEO salary as our dependent variable salary. We can take the mean of that very easily. And then our predictor is gender with two levels. So if you want to kind of use a different predictor, if you want to use more than one predictor, if you want a predictor with 3 levels, we're not able to use a t-test for that. We'd need to use a different statistic. So we'll also cover 2 types of t-tests during this lecture. There's multiple types of t-tests and some variations that your textbook talks about, but we're really going to focus on the independent samples t and the paired samples, sometimes called dependent samples. So which of these 2 tests that you choose really depends on the research design, specifically whether it's a between or within subjects design. And we'll get a little bit more into what those terms mean and talk about some examples. Up until this point, we've spent some time talking about the normal curve, and we also talked about the z-distribution or z-scores. So you can see the purple curve at the top represents our standard normal distribution. One thing that's interesting about the t-distribution, or computing a t-test, is that the shape of the distribution will depend on the size of our sample in our study. So I've alluded to this a little bit previously and in other videos that sample size is really important for our statistics, and in general, the higher the sample size, the larger the sample size, the better our statistics are able to run, and the more likely it is we'll find a significant result if one exists. So you can see here we have a couple of different t-distributions, and these are based on what we call degrees of freedom. So our degrees of freedom, I said before that it varies a little bit from test to test how we calculate it, but we talked about it being the number of people in our sample minus 1. So you can see the green curve, we have a t-distribution for 2 degrees of freedom, which would be a sample of 3 people. And you can see that that curve is really spread out and kind of compressed down. It's not quite mapping onto that standard normal distribution. You can see though, however, the more degrees of freedom or the more people we have in our study, the closer that curve is going to mirror the standard normal distribution. And again, we said we like the normal distribution because it allows our z-scores to work and allows us to compute percentiles and all of that good stuff that we've covered up until this point. So the key takeaway here is to know that the t-distribution will change ever so slightly depending on our sample size, and in general, the more people we have, the better in this case. So a larger sample is going to give us a more robust test, and it's going to more closely mirror that normal curve. Let's first take a look at the independent samples t-test. So the independent samples t is used to compare two means in a between groups design. So what this means is that the groups or the conditions are independent from each other, meaning that each participant is only in one condition or the other. So I sometimes think of this as kind of the classic experimental control design. So maybe you have a drug that you're testing out its effectiveness. So you have the treatment or the drug group, and then you might have a placebo or a control condition that does not receive a drug. So again, remember that at this point, we're kind of constrained to only two groups. So I am not able to look at drug A versus drug B versus placebo. We can only have two groups at this time. So you can think of other groups. Again, we have to have two of them. They have to be measured in a nominal way. So gender is another good one, looking for gender differences. You could look at differences in political opinion based on Democrat or Republican. You could look at differences in children's ages. You could compare 13-year-olds to 15-year-olds. But again, recall that we're constrained by only two groups of people, and you cannot be in more than one group. You have to be in one condition or the other, which is why it's an independent samples t. Here you can see a little visualization around the independent samples t. So really we're drawing two separate samples from two different populations. So as an example, maybe I'm using a new teaching methodology. I have population A. I have a group of students that are going to be taught by a specific teaching method. I could pull a sample out of that population. Similarly, I could repeat the process for a second population taught by a different instructional method. So in this case, I don't know what the population mean is for those two different populations. I'm kind of just limited to what I have here with the sample. But ultimately, we're comparing sample A and B, and we want to know if those are drawn from two distinct populations, whether they're really different from each other when it comes to their means. So let's take a look at the homework that we did in the previous week. We looked at salaries from male and female CEOs, and I had you run some basic descriptive statistics on them, both as a whole and both split out by gender. So really, the independent samples t-test is allowing us to take that next step and ask ourselves, are these two salaries statistically different from one another for male and female CEOs? So we have two separate samples. We have a sample of female CEOs, a sample of male CEOs. So the data set from last week, I think we had 60 different Fortune 500 firms. I've condensed this down quite a bit just for the sake of having a short little example here. So you can see at the top, I have a group of female CEOs. I have 4 of them in my sample, and their salaries are reported in thousands of dollars. So you can see 150,000, 230,000, 280,000, 340,000. So if you take those 4 salary scores, average them together, we get a mean female salary of $250,000 per year. Not too shabby. Same thing with the male CEOs. You can see here I have a sample of 5 male CEOs. You can see their individual salaries, and you can see that their average salary is $400,000 a year. So at this point, we can set up our null and our research hypothesis. So if you remember from the previous lecture that our null hypothesis is always saying there's nothing going on, there's no difference. So our null hypothesis for this example could be that on average, female CEO salary will be the same as male CEO salary. Or you can see the notation there in the symbols. Our null hypothesis means that mean 1 equals mean 2. Now, our research hypothesis, there's a couple directions we could go with this. Your book talked about one-tailed versus two-tailed tests. For the purpose of this course, we will only use two-tailed tests. So I could say something like, on average, female CEO salary will be different from male CEO salary. Or you can see in the notation there, the means will not equal one another. So a one-tailed test might be putting a direction on it. I could say on average, I think that female CEO salaries will be lower, or I think that they'll be higher. The two-tailed test kind of protects us though, because we're keeping our options open, especially if we don't know which direction of an effect we might find. So the two-tailed test is simply saying that our means will not equal each other. So you can see just looking at this data, this small sample here, that the mean of 250 and the mean of 400, those definitely do not equal each other. They're different. But the question that our t-test will help us answer is, are they significantly different? You could imagine a scenario where the female CEO salary is maybe $250,000 and the male is $252,000. Those seem pretty similar to one another and they probably aren't different. But the question we have to ask is, how far of a spread do we have between those two salaries in order to conclude that there is a statistical difference between them? And instead of just eyeballing it, we can actually calculate that and run the statistical test to test this hypothesis. Here we have the actual formula for calculating an independent samples t-test. So this is out of your textbook, and you can see it's not too bad if we were going to do a hand calculation. You can see that our t statistic is equal to the differences between the sample means on the top in the numerator there. And then the denominator is the standard error of the difference between the means. So your book walks you through how you can calculate this out by hand, and if that helps you understand it at a conceptual level, I strongly encourage you to walk through that example in the text. But really what we're doing is we're taking the difference on top between the two sample means, and we're accounting for the standard error or the difference between the means on the bottom. So we'll notice this as we go through and run other tests, but a lot of our statistical tests have to do with some measure of difference on the top and accounting for some error measure on the bottom in terms of our numerator and denominator. And you can see actually this t formula, it might remind you a little bit of how we calculated z-scores. Because if you recall, to calculate a z-score, we took the individual raw score, subtracted a group mean, and divided by standard deviation. So we said before that standard error is really kind of a different version of standard deviation because we're talking about how spread out scores are. So the formula is not too bad if you wanted to try calculating it by hand, but again, for the purposes of this course, we really want to focus on how we can use SPSS to save ourselves a little bit of time and energy. So you could calculate this by hand. I'll show you in a minute how we can calculate it in SPSS, but kind of the follow-up question once we have this t-test statistic calculated is, how do we know whether or not it's considered statistically significant? So there's a table in the back of your textbook, Appendix B, and as I said before, that slide with the different colored curves and distributions on it, the shape of the t-distribution will change based on sample size, and that will affect your significance cutoffs, or whether or not something's considered statistically significant. So this table can be a little bit unwieldy to look at on first glance, and I'll try to walk you through it to simplify it a bit here. So you can see at the very top it says alpha level for two-tailed test, and it has some values underneath it. And then we have kind of a layered table here where it says alpha levels for one-tailed test. So again, what kind of test are we going to use in this class? We're only going to focus on two-tailed tests. And I think I said in a previous lecture that we'll always use an alpha level of 0.05. That's kind of our scientific convention that we tend to use. So if I pick alpha level for two-tailed test, 0.05, you can see it's that middle value there. And I'll just drop down and focus on this column right here. So a 0.05 two-tailed test corresponds to a 0.025 one-tailed test, just so you know how they fit together. But again, we won't be running the one-tailed test. You can ignore that for now. So you can see our column that we want to focus on here for our two-tailed 0.05 test. So really the only thing we need to determine a cutoff or what's considered statistically significant is we have to find the degrees of freedom. So I said before that degrees of freedom is the number of people in our sample, subtract 1. And for an independent samples t-test, we're going to morph that a little bit because if you noticed, we had 4 women in our sample and 5 men in our sample. So our t-test does allow us to compute t-statistics for groups of different sizes, which is really convenient because you don't have to worry about having equal sample sizes. So to determine our degrees of freedom, we want to take sample 1, or the female CEOs, the total number of people in that sample, subtract 1. So we had 4 in there, 4 women, minus 1 gives us 3. And then we want to do the exact same thing for our second sample of men. So for men, we had 5 men minus 1 equals 4. So we have 3 degrees of freedom for the women's sample, 4 degrees of freedom for the men's sample, and all we want to do is add those together. So 4 plus 3 equals 7. So we're at 7 degrees of freedom. And if I just draw my cursor over here to this column we wanted, we see that my critical value for 7 degrees of freedom is 2.365. So we have that critical value, and again, it's nice to use the table to kind of understand where these numbers are coming from, but SPSS is going to actually know all of that because it's going on in the background when it's running the program. So you can see here, this is kind of our decision normal curve, and all I've done is drop in those critical values, either on the positive side or the negative side. So our 2.365. So, and you can see that this corresponds to about 2.5% in each tail of our curve for a total of 5%. So we said before that 0.05 or 5% is the cutoff that we use. We kind of acknowledged last time it's a little bit arbitrary, but it's kind of the best that we have to deal with when we talk about social science research. So we can compute our t-statistic, and if we find that our t-statistic exceeds this critical cutoff of either 2.356, either positive or negative, then we can reject the null hypothesis, and we would say there's something going on. These sample means are definitely different from each other. There's a real significant or meaningful difference happening. So we can do this in 2 different ways. We can either calculate it by hand, or I'm going to jump over to SPSS and show you how we can run it using SPSS. Here we have SPSS open. I went ahead and entered the data just from the slide. So if you want to try this at home and follow along, definitely feel free to do that. Right now I'm in my data view, so you can see it looks like a Microsoft Excel sheet, and I've entered the salary data for men and women. I'm going to click under variable view really quick here and give my variables names. So my first variable was gender. My second variable was salary. These copy and pasted as numeric, which is great. For gender, I can go ahead and click on this blue box with the 3 dots under values, and this will allow me to label and tell SPSS how I coded gender. So in this instance, I coded males as 0 and females as 1. So I'm just going to type that in, hit add, and then OK. So you can see in this measure column, SPSS, I'm telling it that gender is nominal, or it's a categorical variable, and salary is scale because it's something that we're going to be able to take the average of. So now if we jump back to our data view, we can see that SPSS input our labels. So we have gender and salary, and we want to know if there's a significant difference between men and women on the salary variable. So I'm going to go to the Analyze menu, and up until this point, we've really been working in this Descriptive Statistics menu. So we're going to jump down one more menu to Compare Means, and this is where our t-tests and also our one-way ANOVA commands can be found. So I'm going to do Compare Means, and I'm going to select Independent Samples t-test. So you can see here, I'll go ahead and reset this so we can start from scratch, but it has all of my variables available in this left-hand column, and all I have to tell SPSS is what is your test variable or your dependent variable, and what is your grouping variable or your independent variable. So we said that our DV will be salary because we can take the average of it. And we said we want to know if salary depends on gender, which will be our grouping variable. You can see when I transport gender, though, it has these 2 question marks, and there's this button that says Define Groups. So we have to tell SPSS what labels we used in order for it to read our data correctly. So I'm just going to click on that Define Groups button. And here is where I can say that group 1 was women, we labeled it 1, group 2 was men, we labeled it 0. So again, it doesn't really matter how I labeled these. If I labeled it +1 and -1, if I labeled it 99 and 98, you just need to tell SPSS how they're labeled. And then we'll hit continue and OK. So now we have an output window that's open from SPSS. Again, you can see here at the very top, these are just the computer commands saying what we ran. And then we have our t-test results. You can see this first box called Group Statistics. This is a little similar to what we did for your homework last week. We have salary for females, salary for males. We have N is the number of people in each group, and we have the group means for each of those. So that 250 and 400 should look familiar because that's what was on the slides that we could have taken the mean of. It's also gone ahead and computed standard deviation and standard error for both of those groups. So really this first box is everything you would need to plug into your t-test equation if you wanted to solve for this by hand. But SPSS was really nice and it actually solved it for us in the second table here labeled Independent Samples Test. So you can see here, there's two different rows that we can look at, and I want to say a little bit about what this means. So I mentioned before that when we run an independent samples t-test, we don't have to have equal groups, equal group sizes. So we see that we have 4 women and 5 men. We didn't need to have equal sample size. So that's okay, but instead of having equal sample size, one thing that we want to check is that the variance within our groups is roughly similar. If we had a high degree of variance for the women and a low degree of variance for the men, that might throw off our calculations a little bit. So one of the assumptions that underlines the t-test is that even though you may not have equal group sizes, you have roughly similar distribution or variance within those groups. So again, SPSS is nice, it's looking out for us, and it actually runs a check for that assumption. And that's these first two columns called Levene's test for equality of variances. So you can see here the top row, it says variance is assumed, and it's actually running a short little statistical test to make sure that those variances are roughly equivalent. So that's represented by the letter F, and then it has a corresponding significance represented by this column labeled sig. So in this case, because we want equal variances, we don't want to find a significant F test. And you can see here our F is 0.961, the significance is 0.360. In order for this to be considered significant, our significance column would have to be a number less than 0.05. So in this case, we can reject the idea that there's something going on with our variances. Our variances are roughly equal, which is a good thing. So in this case, we can just continue along the top row to interpret our t-test results. If for some reason our significance was less than 0.05 in this column, we would just jump down to the second row that says equal variance is not assumed, and we would pull the results off of that row. So I would say 9 times out of 10, it doesn't make a difference, even if there is something wonky with your variances. Whether or not you find a significant T, it tends to come out the same either way. But it's always a good kind of data screening procedure to take a look at. So I'm going to continue on this top row. The equal variance is assumed. You can see a calculated T statistic we have here. We have negative 2.436. It's a 7 degree of freedom test, which we know from looking up in the table in the back of the book. And it's given us a significance test, and you can see we're at 0.045, which indeed is less than that cutoff of 0.05. So it looks like we have a significant difference between men and women on salary. It tells us that the mean difference is roughly $150,000 in salary, which is a pretty good chunk of change. It also calculates a standard error for that difference. And the last two columns here is our confidence interval, which we talked a little bit about previously. But what this is telling us is that we can be 95% confident that the difference in salaries for men and women, it's going to fall somewhere between negative $295,000 and negative $4,000. So it gives us that band that we think that this true mean difference value might fall in and how confident we are. So this is exciting because we see that we had a significant t-test. Again, that negative 2.436, 7 degrees of freedom. It's significant at 0.045, which is less than 0.05 for our alpha level. So let's jump back to the slides and take a look at what that means. Here, going back to the slides, you see I just have kind of some shortcut commands, how we got to that independent samples t-test menu in SPSS. There's also a handout that I posted online that details that with some screenshots, so that should be helpful to you as well. So now we have to make a decision, and we said that we found a t-statistic with an associated significance value of less than 0.05. And you could see we could actually map this out on our normal curve here. So this was our critical cutoff, kind of our rejection region that we've drawn in the purple. So our critical cutoff, based on the back of the book table, was negative 2.365. And what we calculated from SPSS was negative 2.44. I just rounded that to 2 decimals. So in that case, you can see in the blue words down here how we might write this up using APA style. In this case, male CEOs had significantly higher, and I put the average salary in parentheses there, the mean. They had significantly higher salaries than female CEOs with their mean as well. I want to include the t-statistic with the degrees of freedom in parentheses. The actual t-statistic SPSS calculated, and then p less than 0.05. Sometimes in articles you might see an exact p-value reported, so we could have said p equals 0.045. It gives a little bit more precision, but we really just care whether it's less than 0.05 or not. So that's an example of how we're able to look at two different group means from two different independent groups. In our case, we had even different group sizes going on, and determine whether or not those means are considered different from one another. And in this example, it does look like the men have significantly higher salaries compared to the women. Moving on to paired samples t-test. Sometimes you'll see this referred to as dependent samples t-test. The design is very similar here. Again, we're comparing two sample means, but in this case, we're using a within groups design, as opposed to the independent samples, which was between groups. So the major difference with the paired samples is that we must create different scores for each participant. So there's several ways you can use a paired samples t-test. I think one of the most common is a pre-test post-test design. So you see this a lot in education, tracking progress of kids over time. You see this a lot in medical research, seeing how a patient might improve using different interventions or treatments. But the idea is a lot of times we're following the same person over a period of time. Now you can also do some variations on this where it's not necessarily over time, but you're comparing attributes within a same person. So if you think of something like test scores in math versus test scores for English, you might have a student that has test scores for both of those, and if you want to compare that student's English to math, that comparison is being made within kind of at that individual child level. So that's another example of the the paired samples design that isn't quite a pre-test post-test, but we're making comparisons within subjects or within groups. So your book gives an example about calculating how employees make widgets and whether or not that improves when they get back from a vacation or not. I have a slightly different example here. In this case, we're interested in how volunteers perform a set of tasks under two conditions, using a 15-inch computer monitor or a 42-inch computer monitor. So in this case, I have the same people in my study. I run them through asking them to do this task on a smaller monitor, and then I switch the people over to use the larger monitor, and I see how their performance changes across time in those two conditions. Now, the thing that sometimes makes t-tests a little confusing is because you could also imagine how this specific example could be run with an independent samples t-test. Suppose I took my group of 15 volunteers and I cut the group in half. Maybe I had 7 people in one group, 8 people in another, and I had them do the tasks using the two different monitors and different people in each group. That would be our independent samples T. But in this case, I have 15 people and I'm having them use both conditions. So complete the tasks under both the 15-inch and 42-inch monitor conditions. So that makes it a paired samples because it's the same people being tracked over time and conditions here. Again, our null hypothesis is always saying there will be no difference. So you could say something like people who use the 15-inch monitor will complete tasks in the same amount of time as people using the 42-inch monitor. So our means would be equal regardless of which condition you're in. The research hypothesis, on the other hand, is just going to say that people using different monitors will complete the tasks in a different amount of time. So the means will not be equal to each other. Again, I don't want to guess if they'll do it faster or slower and put a direction on it. I'm going to keep my options open and use that two-tailed test. And all I'm saying is that they'll complete the tasks in a different amount of time. So I have some made up data here. I have the 15-inch monitor, the 42-inch monitor, X and Y, and all I've done is create a difference column. So you can see here this is measured in seconds, how quickly they're completing this task on the computer. And you can see that I've taken across the samples here and I have computed the average difference between the two monitors as 11 seconds. So according to our null hypothesis, there should be no difference. So we would expect X and Y columns to equal each other. You subtract them, you'd have a mean difference of nothing. So again, we know that this difference is not equal to 0, this negative 11. It's definitely not equal to 0. But again, our question is, how different does it need to be in order for us to reject the null hypothesis? You can imagine if the mean difference was just 1 or 2 seconds, that's pretty close to 0, and we might think there's nothing really going on and the monitor doesn't make a difference. On the other hand, if we have 11 seconds, that could be a significant or an important change. So we want to actually run our paired sample t-test to test whether or not that makes a significant difference. Very similar to our independent samples t-test, we have the formula for calculating the t-statistic. So again, X bar is the time using the 15-inch monitor, Y bar is the time using the 42-inch monitor, and on the bottom of the equation, I have the standard error of the difference between the means. So again, there's a measure of mean difference on the top and a measure of error on the bottom, and that's what's being used to compute our t-statistic. I'll want to compute my degrees of freedom just like before. So same formula, I'm taking the number of people and time 1 and time 2 in this case, subtracting 1 and adding those together. And then you can see here that I've looked up the critical value based on a two-tailed test and a p-level of 0.05 for 4 degrees of freedom, and I end up with 2.776, either positive or negative. So again, that's going to be that cutoff point for whether I should reject or fail to reject my null hypothesis. And all we need to do at this point is calculate our actual t-statistic and compare it to that test cutoff value. Jumping back to SPSS, I've created a new data set here. So again, I've just taken the numbers from the slides. We have the 15-inch, or I've called it small screen, the 42-inch, I've called it large screen. And I went ahead and just entered the number of seconds for each of those values. You can see under variable view, I've given them names, double check that they're numeric, and for measure, we'll tell SPSS that these are scale. So it's something we're able to take the mean of. You notice here that the setup is slightly different from how we did the independent samples t-test because my data are in 2 columns. So I could have called this test 1, test 2, A versus B, but for the dependent or paired samples t-test, we want our data to be in 2 different columns like this. So to run our paired samples, again, we'll go to the Analyze menu, Compare Means, and we'll drop down in this example to Paired Samples t-test. It's right below our independent samples that we just worked in. So this one is pretty easy to input. You can see I have my variables to choose from on the left-hand side, and all I have to do is tell SPSS how I'd like to pair those. So I'm just going to move the small screen over, the large screen over, and once I have those pairs defined, I can just hit OK. So no options or anything else we need to mess with. This one's very quick and easy to run. So I went ahead and hit OK, and that opens up some output in my output window. You can see it gives us an overview. So we have the group means for both the small and large screen. We had the same number of people because it was 5 people over time. I have a standard deviation and a standard error for each of those times. It also, the second box here we can ignore. It just gives you a correlation between time 1 and time 2. That's not really interesting to us at this point, so we'll just kind of skip over that. And then if we go down to the last box, our paired samples test, here we have our first pair that we tested, small versus large. We had a difference of about 11 seconds. We have a standard deviation, a standard error, our confidence interval, and here we have the t-statistic towards the right hand of this table. So we have a calculated t of 5.719, 4 degrees of freedom, and the significance associated with that is 0.005. So again, we'd like that number to be as small as possible, specifically less than 0.05. So 0.005 is definitely less than that. So what we're seeing here is a significant difference in how people perform this task, how quickly they performed based on the small or large screen that they used. So we'll jump back to the slides and see how we might be able to write that up. Again, going back to the slides, here's some shortcut commands in SPSS. Again, we're under the Analyze menu, Compare Means, Paired Samples t-test, and all we had to do was transport and pair them up and hit OK. If we were to take our curve, and again, we've mapped out the critical cutoffs based on 4 degrees of freedom of 2.776, either positive or negative. That calculated t that we found of 5.72, you can see that's way out here. So that's telling us that the difference between those 2 times, or the 2 different screens being used, is quite large. It's definitely considered statistically significant. So in this case, people were significantly faster using the 42-inch monitor than the 15-inch monitor. And you can see I've reported the group means for both of those. I've reported the degrees of freedom, my calculated t-statistic, and my p-value of less than 0.05, or I could have said p equals 0.005. So again, you kind of see both depending on what kind of journal you might be working in. So those are the 2 main t-tests. Again, the independent and paired samples, you see these a lot, especially in healthcare, education, social science, research in general. Maybe you've seen them in an article recently, so hopefully this helps demystify what some of these symbols and statistical notation means. So again, which test you choose to run really depends on whether you're working with a between or within subjects design. So if you're experimental and control group versus pre-test, post-test. So both of them have their pros and cons. It's really just a matter of which one is going to work best for you in your research. Also, again, it's really important to keep straight our independent versus dependent variable. Remember, for a t-test, our independent variable always has to be a category or a group, and the dependent variable has to be something we take the average of. So hopefully that helps clear that up and keep some of those straight. So that's why we reviewed so much independent dependent variable and units of measurement, because it's really setting us up for success when we go to actually run these tests. So the next logical question might be, okay, I can look for group means based on two different groups, either men and women or time 1 and time 2. What happens if I want to add a third or a fourth comparison? And that's really going to be a nice segue into our one-way ANOVA, which we'll talk about in the next video, and we'll kind of extend this idea of a t-test and see how we can even do more with it and answer more complicated research questions.